Hello everyone and welcome to the channel CSAITTL. Before I begin, I just want to introduce to my companion website. It's bitbytoken.com. Um, Basically, this website is here for different articles on various facets of software engineering. It has core software engineering, data engineering, machine learning, and AI engineering. For each of these assets, we have several fundamental. We have a lot of detailed articles listed on those, how to implement them, different kind of variations of these different. Those articles are pretty detailed. Then next we have sample solutions for each of these. For example, designing a Google Drive or designing Instagram feed that we have tried to keep as comprehensive as possible. We start with functional requirement, NFR, scale estimation. Then we talk about data models. We try to create UML diagrams, and then we have further down sequence diagram. So all in all, we have tried to keep it pretty comprehensive and very detailed. So please do take a look at it and share your inputs on this and your feedback. Thank you so much. Okay, so let's coming back to our system design thing now. Today we are going to we're going to look at a very crucial topic which we call as a tear down, scaling the data layer. If you're ready to take apart the data layer and look closely at how we scale from one machine to a global cluster, you are exactly in the right place. Please remember to like, share, and subscribe to the channel for more engineering insights. Our logic is to start simple. We must understand the atomic unit of the database before attempting to distribute it. Under the hood, we'll trace the evolution from single node query optimization to multi node physical architecture. The critical failure point we want to avoid is premature optimization. Do not bolt on distributed system before understanding the physical limits of your current hardware. The journey will guide you through the practical aspects of building scalable database systems. Let's begin with day 730, 2 billion orders, the monolithic ceiling. As a database grows, even with indexes, it eventually hits a wall. From a logic perspective, at 2 billion rows, query must scan hundreds of millions of rows even with indexes. Under the hood, the table's B-tree index has grown so tall that traversing it takes dozens of disk reads per query. This directly impacts performance. The major failure point is B-tree traversal depth. Backup operation that once took minutes now take hours, blocking all other production operations. This clearly shows the limitation of a monolithic single machine database as data scales. Our first step in scaling is logical partitioning, reorganizing the filing cabinet. The logic here is that it divides one large table into smaller, independently accessible segments. Crucially, the application maintains the illusion of querying a single table. Under the hood, this process relies on three components: the partition key, which determines how data is divided; the strategy, which is the routing algorithm, which direct the queries to the correct partition; and finally, the metadata, which is mapping to physical disk files, which keeps track of where each partition resides. However, there is a critical failure point, which is missing the pruner. Without the partition pruner, the database is forced to open every single drawer, negating all performance gains. This highlights the importance of proper implementation. Let's explore the sorters. Range target continuous data dates, making it ideal for time series log, as seen with this P2 2022, P 2023, and P 2024. List isolates discrete business domain regions for compliance like GDPR, as shown in the EU and the US partitions. Under the hood, partitioning enables partition pruning. For example, a query for 2023 order is routed exclusively to P 2023. The database never opens the other partition. However, the failure point is partition skew. If 90% of queries target recent data, the latest partition bears the vast majority of the load while others sit idle, creating a hot partition that bottlenecks performance. To combat partition skew, we introduce the randomizers. From a logic perspective, hash deliberately scatters rows to spread load evenly. Composite layers two strategies to get the best of both the worlds. Hash partitioning uses a hash function to distribute data into various buckets, making it the senior engineer's anti-skew weapon for random lookup by primary key. Under the hood, this randomizer ensures even distribution. However, the failure point for hash partitioning is expensive range queries. Hash partitioning destroys the ability to prune. For example, a query for last week orders must scan every single partition because the chronological order is lost, making such queries highly inefficient. Even with partitioning, we eventually face the single node ceiling when traffic multiplies by 40x. The logic is that partitions reduce the logical scope of a query, how much data you want to look at, but they do not add compute power. Under the hood, the cabinet still has only one door. All partitions compete for the same CPU cores, memory bus, and disk I/O channels. This leads to a critical failure point: shared resource contention. Massive traffic spikes will exhaust the single server's hardware envelope, regardless of query efficiency. This indicates that logical partitioning alone isn't enough for true scalability. We need to move beyond a single machine. This brings us to the physical sharding, which cross the network boundary. The logic is that sharding equals logic partitioning plus physical distribution across multiple independent nodes. It's about distributing data across completely separate servers. Under the hood, each shard is a fully autonomous database server. Shard 0's CPU usage does not affect Shard 1's throughput, providing true horizontal scaling. However, there is a significant failure point: the router bottleneck. The application never directly connects to shards. If the shard router fails, the entire distributed system goes dark, making the router a critical single point of failure and a key architectural consideration. To address the router bottleneck and enhance flexibility, we use the two-layer model, decoupling data from the hardware. The logic is that a logical shard is named a PO box. A physical shard is the post office building storing those boxes. Under the hood, the routing layer maps data to logical shard IDs first. Then a separate mapping table translates logical shard to physical node. This decoupling is vital. The failure point is always direct 1:1 mapping. In a one-tier model, adding a fourth node forces a full rehash of all the data. However, two-layer allows moving logical shards without rehashing the keys, providing much greater operational flexibility and reducing downtime for rebalancing. Choosing the shard key is an irreversible decision. The logic is that the key dictates data placement. You must design the key around your most frequent query. For example, user ID for user-centric queries. Under the hood, advanced systems use compound shared queries, locality plus time, to co-locate data geographically while maintaining a balance. This is a complex art. The failure point for shard keys is low cardinality keys. Sharding by status, where 85% of records are delivered, forces 85% of traffic to shard 0. You must recreate the monolith and overload and bottleneck on a single shard, negating all sharding benefits. Now, let's discuss cross-shard operations, the scatter-gather text. The logic is that queries spanning multiple shards require a parallel fan-out with a merge-reduce step on the router. An incoming query is fanned out to multiple shards, shard 1 to shard 8. The results, candidate row x80, are then collected and processed by a merge-reduce step. Under the hood, a query that took milliseconds locally now requires 8 network round trips, 8 simultaneous query execution, and router level in-memory sorting. This leads to a failure point: network latency multipliers. Scattering operation across the network exponentially increases the risk of slow responses or partial failures, highlighting the hidden cost of distributed queries. A particularly dangerous scenario is the cross-shard joins, the distributed landmine. The logic is to avoid cross-entity joins at the database layer. Instead, use shard co-location to ensure related data lives on the exact same node. As shown, if node A, which is for users, and node B, which is for post, use different shard keys, joining unjoined data stream users and unjoined data stream post directly is problematic. Under the hood, if tables are use different shard keys, the SQL optimizer cannot perform internal joins. The logic shift to the application layer. This leads to the failure point. In memory, app layer joins. Pulling unjoined partial dataset across the network and joining them in application memory will instantly crash your app under load, as the application server cannot handle the memory and CPU burden. Let's look at the real world teardown. The logic is that Instagram encoded the logical shard ID directly into the PostgreSQL primary key using a custom ID generation scheme. This custom 64-bit ID string included timestamp chunks and sequence byte along with an embedded logical shard ID. Under the hood, because the timestamp is embedded at the front, IDs remain globally sortable by time for feed ordering without secondary indexes. This is a clever optimization. The significant failure point Instagram bypassed is centralized lookup tables. No router lookup table is needed. The shard destination is mathematically decodable from the ID itself, eliminating a common single point of failure and simplifying routing. Another real world teardown. The logic here is native distributed sharding. Data is automatically distributed using consistent hashing. The ring topology is the routing mechanism, eliminating a separate router component. There are no manually managed partition. Instead, a rows partition key hashes to a token within exactly one node's range. This design has handled 120 billion plus messages effortlessly. The primary failure point it addresses is the router's point of failure. Cassandra's or masterless design eliminates the central traffic cop. Any node can coordinate any request, enhancing fault tolerance and scalability by removing single point of failure. Let's examine Vitess and Strangler fig. The logic is, how do you shard MySQL without rewriting the entire application? The solution is to insert a smart middleware layer that fakes a single connection. This VT-gate middleware sits between your application and the sharded MySQL instances. VT-gate intercepts standard SQL queries, rewrites them for shard routing, and manages the scatter-gather complexity internally. The Strangler fig pattern allows you to gradually introduce sharding without a full rewrite. The failure point it addresses is massive application rewrites. Replatforming an app to be shard aware is highly risky. Wrapping the database with a middleware isolates that complexity, making the transition much safer and manageable. Finally, we arrive at our senior engineer decision matrix. The logic here is the crucial takeaway. Don't over-engineer early. Align your architecture strictly to a dominant access pattern. This matrix guides you from a monolith through logical partitioning and potentially to physical sharding. The best architecture use both. Partitioning within each shard to optimize query speed, and sharding across nodes to handle total storage. The critical failure point to avoid is sharding too early. Sharding introduces distributed transactions. The advice is always maximize logical partitioning before taking the physical network penalty, ensuring you get the most out of a single machine before incurring the complexity and cost of distributed system. Please do like, share, and subscribe, and comment on what would you like to see next. Thanks so much. Happy coding. Bye.